Hey, so just to briefly introduce myself, my name is Srinath Kailasa. I'm a PhD student in the maths department at UCL. I work on problems in computational science and specifically taking some of these equations and making them run on computers fast. And one of the things in our group, Timo is my supervisor, so one of the things we've been really pushing is Rust at the moment. So a brief overview, I'm going to go over one of the algorithms that I'm working on implementing in Rust, some of the traits that have been useful when designing this algorithm, a little brief discussion on where we're going to take this project, and some thoughts for the future. So the algorithm is kind of motivated by n-body problems. For example, in gravitation or electrostatics, where you have, say, n particles, and you're computing the potential between all of these particles. And one of the approaches is called the fast multipole method, or FMM. And this basically can take down the ON squared complexity of this to O(n) log n, or even ON in the best case. And the way it does this is by constructing a hierarchical tree and recursing up and down this tree, compressing long-range interactions. This essentially amounts to doing a matrix vector product style calculation, like AX equals B, and A in our case is always dense. So the FMM in some way numerically specifies this and makes it faster to actually apply this matrix. So there have been a ton of different softwares in the past that can compute this kind of problem. The problem with this is they're often designed by people like me, people who are working in the domain, maybe with a specific method in mind. Sometimes they have maybe a specific optimization in mind. And the problem with this algorithm and many algorithms across computational science is that there are so many of them, and there are so many different ways of implementing things, as well as optimizing things, as well as writing things down mathematically. And because of this, it's quite hard to actually design a general purpose software tool that you can iterate on quickly, is also quite performant, and allows you to build upon this when you say implement a new method and you want to try out something else. This leads to a lot of set pieces that are quite good at what they do. I'm not knocking how good some of these FMM softwares are. Some of them are awesome, but it's difficult for someone, say, who hasn't seen the code before or hasn't delved into it before, to go and get stuck in and try and make their own changes and adapt it to their own use case. And this is kind of where the thought for Rust has come from, because it's giving us a platform to, as a small team, quickly iterate on a range of ideas and build out quite general software. So where did this even come from in the first place? So my master's project a couple of years ago now was focused on trying to make Python really fast and seeing if we could get all of this functionality I just mentioned in terms of extendability, usability, and speed by using Python plus Number, which is a JIT compiler based on LLVM. And the basic outcome, like the summary, high-level summary of this, was we could get pretty good using Python and Number, but we couldn't get as much as we wanted out of performance. So okay, let's look at Rust. I think I'm going to skip this because I've kind of already mentioned that. So in terms of the basic traits that we have for this FMM, basically we're able to kind of isolate all of the kind of independent components as trait interfaces. This is not going to mean much to people who aren't in the community, but things like field translations, the integral equation kernels, the distributed trees, which the FMM relies on because you have to go up and down these trees, as well as the actual algorithm implementation. And there are numerous versions of these. The usefulness of this is we can reuse components for different types of algorithms. So the FMM is the forward application of this dense operator, and there are also algorithms for the rapid inversion. And the great thing is they're both based on much the same software. For example, the trees and the kernels and the field translations can be used again. But the problem with current softwares is they're kind of embedded into how they've built their FMMs in the first place, which makes it difficult for them to reuse components in extending their software to new environments. And this is kind of great because what we can do is just impose these trait implementations. And I say like this as if it's something new. Obviously, you could also achieve much the same thing using object-oriented programming. But I guess the real difference is once we've imposed the trait, we can kind of immediately forget about the interface and just look at the kind of low-level optimizations, which is what we're interested in really tuning. When you have kind of objects and quickly extend out into complicated hierarchies, which is challenging to deal with, especially when you have large software projects. as a solo developer or a small team. So I guess this is kind of almost a question. It's not something I'm entirely sure about yet. I've been writing Rust for maybe 18 months now, and I've definitely gotten better at designing trait interfaces, but it's something I'm still developing. And a good example of this is designing trait interfaces for this field translation component. This is the biggest computational bottleneck. And I found in writing my own code that there's sort of a trade-off in between how much you can specify in an interface and how flexible you want the trait to be for an implementer to tune the performance in that specific operation. For example, I mentioned this hierarchical tree. These field translations are applied over all of the nodes at a given level of the tree. So one way of doing it would be to, say, write an interface for the operation on each box on its own. Another way would be to do it over the level. But each of these has a trade-off in that you want to, say, maximize the reuse of cache. So you kind of want to pull in all of the data for the whole level at the same time and go through it sequentially, in which case your trait is kind of a bit more abstract than you might like it to be. It's operating at the level of an entire level of this tree rather than a single box, which makes it more difficult for, say, someone to come in and maybe change the algorithm that's being used. Which kind of, yeah, it's this trade-off that I've noticed while implementing my own traits. It's you want them to be as general as possible, but at the same time, you are kind of constrained by the optimization you're trying to build in. But yeah, this is definitely a work in progress. But I wanted to conclude with a bit on resilient software, and this is why I think Rust is still really good, despite some of these trade-offs. One is I've never really had a huge amount of experience with C++. I kind of grew up with Python in my undergrad, and then in my master's we did a little bit of C++, and through my PhD it's just been Rust. But even with my brief C++ experience, my developer experience in Rust is awesome. For example, the installation, extension, and maintenance of all the stuff is super easy with Cargo, and this makes it really awesome as a domain scientist to use Rust. So despite some of the trade-offs, I think my experience has been massively positive, and I've been able to be quite productive using Rust alone. Yeah, in the future, we're going to extend out this software to multi-node environments and different algorithms, and also the rapid inversion as well. But this is still very experimental code at the moment. But yeah, feel free to follow us on GitHub at bempp/bempp-rs.